Right. Welcome to Maths Linear Algebra. Today is the 29th of October. We're going to do tutorial 7. Before I do that, I make some announcement first. I've already answered tutorial 7, question number 5, part 17 and part 18. And I've recorded them and I've put it out on YouTube. So please go to tutorial 7 playlist in YouTube and you will see it there. So I would immediately jump to question 6 of tutorial 7. So this is tutorial 6 of question 7. There are 3 parts to the question, which is part number 19, part number 20, and part number 21. The questions basically examine the following. Given a matrix A, which is not square, n by n, and we are saying that the following statements are logically equivalent. We begin with the equation we want to solve, which is ax equals to b. By now, please remember that we do not, or we may not have a consistent equation such that ax may not be equals to b. What we are trying to find is that we are trying to find ax hat such that it will be b hat, such that b hat minus b, the norm, is as small as possible. And we are using the Euclidean norm, means the Pythagoras theorem norm, or the length. Now, given that, the solution that we found with this condition is called the least square solution. When we talk about a solution, we're talking about the variable x. What is the solution is what is x such that ax hat equals to b hat. Now, the question asks the following. He says that the following 3 statements are logically equivalent, meaning that if I tell you one of them, the other 2 are automatically true. So maybe this one is the easiest to understand. The columns of A are linearly independent. We now remember that A is always a column, or sorry, a matrix. And we can think of it as, for example, a 3 by 2 matrix. Maybe we only have 2 columns and we have 3 rows. So this is A. If A1 is not, is in A1 and A2 are linearly independent, that means A2 is not dependent on A1, it is not found by a linear combination of A1, then the columns of A are linearly independent. That's what it's saying in this 14b. Now, if this is true, and we like it to be true, then what happened is the following. ATA is invertible. What is ATA? If this is A, then what is AT? AT is actually the same 2 columns, but now it is being laid on its side. So we have A1 and A2 like this. And now if we have ATA, what we are having is actually a 2 by 3 matrix multiplying by a 3 by 2 matrix in our particular example, then we are getting a 2 by 2 matrix of ATA. What it says is that if the columns of A were independent, this matrix ATA is invertible. And when this matrix is invertible, then what we can do is that we can plug it into this equation to find x hat, the least square solution. If this is invertible, we can find this. ATB is nothing but plugging in the AT value multiplied by B. Since this is invertible, by invertible matrix theorem, the columns of this matrix is independent. And not only that, when we do row reduction, then we would get a unique x hat. And that is the answer. So I went to one big, very fast exposition of this discussion. And maybe whichever way you like to understand it, they are all logically equivalent. Now, I will go through the proof 19, 20, 21. But before I do that, I would like to point out to you this website.
Sorry, Prof. We can't see the screen.
Oh, you can't see my screen? I'm not sharing my screen? Oh, my goodness. So I've been talking and I'm... All right, sorry guys. Then let me do this again. Oh, how come? Okay, the problem is I can't see what I'm doing. Am I not sharing my screen? Okay, am I sharing my screen now?
Yes, Prof.
Okay, so I've talked about 5 minutes and you didn't understand what I was talking about. Okay, never mind. Let's do this again. All right, let's try. How I am sharing my screen. You guys can see my screen. Let's start. Okay, we're doing. Let me collect my thoughts then. Maybe I'll just record this and then it'll be easier. Okay, let's just do this very quickly. In question number 6, okay, I'm sharing my screen. Okay, let's do this. Now, this is tutorial 7. I've done question 1 to 4 in the past. And then very recently, I've recorded question number 5, part number 17, and part number 18. So go to the playlist and you watch that, please. What that means is that we only have tutorial 7, question 6 left. This is tutorial 7, question 6. So we have already answered question number 5 in the video. All right. But since I have cocked it up, I'm going to record this and then I'm going to put it up as well so that we don't waste time. Now, but what is the big picture of this question? The big picture of this question is this. I'm going to solve AX equals to B. And when I'm given A that has linearly independent columns, then the following 3 statements are logically equivalent. That's what it's saying. The columns of A being linearly independent is a very easy thing to understand. It basically, let's have a clear example. Let us have an example of A being a 3 by 2 matrix. It's when A has linearly independent column, it means that the columns of A1 and the columns of A2 has nothing to do with each other. I cannot make A2 to be some multiples of A1. A2 and A1 are independent. A2 cannot be formed by some combination of A1 or some multiples of A1. Right? If I have A, I can form AT, and AT is nothing but a transpose of A. So if I have a 3 by 2 matrix, then the transpose is a 2 by 3 matrix. I can multiply AT by A. What it means is that AT is a 2 by 3 matrix. A is a 3 by 2 matrix. Therefore, ATA is a 2 by 2 matrix. It is a square matrix. The question now is this matrix invertible? And if it is invertible, then of course we can do something about it. So the third condition given to us, or the third statement given to us, is that yes, if A has linearly independent column, then ATA is invertible. And when ATA is invertible, we can actually plug it in and solve for this guy. Once we can solve for this guy, ATB can be solved because A is given to us, B is given to us. ATB is nothing but the multiplication of these 2 matrices. We can solve for this, we can solve for this, and therefore we can get X hat. And X hat is called the least square solution. Finally, the question then asks, is the least square solution, the x hat found by this equation, unique? And the answer is yes, it is unique. There is no other x that will be able to, that you will get the best approximation to. Okay, approximation of what? All right, the idea is we start from the beginning again. We are given A and we are given B. The question asks, let's find a x such that AX equals to B. And typically the problem is an inconsistent equation. We will never find an x such that AX equals to B. What we then hope is to find x hat such that we can do A multiplied by x hat equals to B hat. And because we are doing A multiplied by x hat, we're actually finding combinations of the columns of A. And therefore B hat lies in the column space of A. That's all. And B hat found by the least square solution is that the norm of B hat minus B, meaning that the error, the residual, is the smallest in the least square sense. So the square is this square. The least means the smallest that I can ever achieve. And therefore, that was what we have been talking about in the past. Now, this problem has been examined by this book, Interactive Linear Algebra, Georgia Tech. They put up a nice online book up, which you can take a look at it. In the middle of this chapter, which is chapter 6.5, you will see exactly the same question as we are being asked now. It says that this is the theorem, Ax equals to B has the least squares unique solution. Columns of A are linearly independent, ATA is invertible. The proof, only about 10 lines of explanation. So you can read that. In my recordings, I would go through part 19, 20, and 21, also to answer the same set of questions, but in a more verbose form. But if you understand this, then you are getting the proof. Okay, so with that, I think I have sort of answered the main part of this question. So instead, maybe now I will take the time to help those guys going into the lab. So let us now see the lab menu. In the lab menu, which will begin this Friday for FS3, this is the question that is being asked. There are two questions, 4A and 4B. 4A is talking about least square solution. 4B is nothing but some matrix algebra trying to solve some complicated matrix algebra with random valued matrix. So let's begin with 4A. All right, let's try to understand 4A. I'm going to write my description here, and anytime you guys have a question, please stop me. So we have a an M by N matrix. And typically we want to have more rows than column, but that is not always the case. We are given B, M rows, so that we can find AX equals to B if that is possible, if there is such a solution. Okay, if it does not exist, that means if B is not a linear combination of A, then find the least square solution. So we are back to the problem of, let's find AX hat equals to B hat such that B hat is nearest to B. Answer the following questions. The first one is pseudo inverse. So we are wanting to find P inverse. What is P inverse? So you have already understood A multiplied by his inverse is equals to the identity. The inverse multiplied by A is equals to the identity. What is P inverse? P stands for pseudo, and sometimes called the Moore-Penrose inverse, Penrose inverse. And it is typified by the notation A plus. The pseudo inverse of A is A plus, not A minus 1. Okay, so that is the typical. And how to find this guy? What is A plus of A? So if you want to use, what do you call it? If you want to use Python to do it, I'm going to give you the code now. So I set an A. I let A equals to 1, 2, 3, minus 4, 5, and 6. What is A plus? Okay, first is A is a 3 by 2 matrix. A plus is a, so first and foremost, you guys will be wondering, right? Inverse only exists for square matrix, which is true, but pseudo inverse exists for rectangle matrix as well. Of course, if it is square, there's no problem. Okay. Now, so what is A plus? So A plus is actually a 2 by 3 matrix. So what you realize is that later on, I'm going to play with A plus times A, and I have a 2 by 3, 3 by 2, and then you will get the identity, which is a 2 by 2 in this example. All right, let's play. So I'm going to just run the code. So I've initialized A here. I've initialized B here. And I want to show you how to get the P inverse of A. We'll just use NumPy's linear algebra P inverse. So in MATLAB, it is simply P inverse A. This is MATLAB. In Python, it is numpy.linear algebra.p inverse of A. Now, we're teaching you P inverse because in the engineering world, actually, everyone just forget about inverse and just use P inverse because P inverse is a numerically more stable version of inverse. If the inverse exists, P inverse will exist and give you the same value. If inverse does not exist, meaning A is singular, then P inverse will give you something too. Okay, so we'll come and see that. All right, let's try. Let's run the code. So let's match. I'm printing my A here. Sorry, I'm assigning my A. I'm assigning my B. I am calculating my inverse of A using NumPy's linear algebra P inverse. I'm printing my A. I'm printing my P inverse. And I am showing you P inverse A times A, which is what I'm going to tell you here. This is P inverse of A times A. And then I'm going to show you one more, which is A times A plus. This is A P inverse of A. So this guy is a 3 by 2. This guy is a 2 by 3. Therefore, this guy must be a 3 by 3. Let's take a look, guys. All right. A is 1, 2, 3 minus 4. So this is what we expect. So now I make green color here. So this is the first step. I'm okay. I'm showing you the P inverse of A. This is the second step. It is a 2 by 3 matrix. Okay. I see a 2 rows, 3 columns. Great. What about number 3? I am multiplying by P inverse times A. I get my identity. That's correct. And finally, I'm doing A times P inverse, which is 3 by 2 multiplied by 2 by 3. I get 3 by 3. I get some funny value. Nothing to do with identity. All right. Now, but it has some meaning. It is a projection matrix. And please read about projection matrix. You have done projection matrix before. QR, Q times Q transpose is the projection matrix. And you'll realize that it is symmetrical. And this matrix, when it multiplies by itself, remain itself, he is actually going to be used to project any vector into the column space of A. All right. So within these 4 lines of code, we are answering part of the lab, or at least I'm showing you how to get part of the lab. Now, for those students, actually, what you realize is that I have given you 4A and 4B MATLAB code in the release of linear algebra. So please go to content, part B, and part B, you'll see lab 4 here. You will see that I keep on updating my tutorial tools, tutorial 7 supporting, and when tutorial 8 comes along, I'll release it here as well. So today I just released this code, test P inverse, which is the code I'm showing you now. You can play with it at home. Previously, I only show you the MATLAB version of how I solve for lab 4. So in fact, if you go to the lab 4, Q4A, you realize that I solved the entire question. Okay, so what it means is that I've shown you how to do it using MATLAB. All I'm asking you to do is how to do it in Python. Okay, and today I show you how to do pseudo inverse in Python. All right, so maybe with that, so we now know how to solve for this guy. Okay, solve for x using pseudo inverse. I'll show you the code now. So the next line of code is here. This is how to get x, the solution of x. So what is we're trying to do here is this. So I'm going to write the problem here. So we know that our problem is we are given A. We are given B. Find x hat. First, using pseudo inverse for the question number 4A. So we write the equation AX equals to B, A plus AX equals to A plus B, where A plus equals to the pseudo inverse of A. So far, okay? Now remember, A plus A is identity. I've already shown it to you. Therefore, X, I should write the small little bracket here. This is the pseudo inverse solution, is equals to A plus B. So if I want to write the code for this, the code is nothing but the pseudo inverse of A is the NumPy linear algebra pseudo inverse A multiplied by B. Finish. So this is the solution. And now I'm going to run and you'll see the solution. Solution is in our example was A is 3 by 2. X is therefore 2 by 1. Our friend here is B is 3 by 1. So I've just calculated X. Again, I've written and mumbled to myself. Okay, so this is what I'm talking about. Right. Now, guys, if you catch me mumbling to myself, it's because I'm looking down into my iPad and writing, and then I did not know that I'm not projecting it to you. So please just warn me, okay, not to do something so silly. Can? All right. So we are getting this now, and then now let's try the second part of the question, which is solve using normal equation. So how do we solve using normal equation? So we start with, again, AX equals to B. The normal equation is, instead of A plus, we are now doing A transpose AX equals to A transpose B. This is the normal equation. And then we want to solve for X. So what do? We A transpose A, we take the inverse, and we hope that it exists. Now, if this exists, this guy reduces to identity, and therefore X is equals to A transpose A transpose B. Now let's see the size of a 3 by 2 A. So for example, A is equals to 3 by 2. Therefore, this is 2 by 3, 3 by 2. The inverse is a 2 by 2 matrix inverse. This guy is a 2 by 3. This guy is a 3 by 1. This guy is a 2 by 1. So finally, X is a 2 by 1. Okay, so this is what we are expecting. And in fact, if columns of A's are independent, you'll realize that what we found here is exactly the same as the pseudo inverse solution. Because the pseudo inverse solution is also a way to find the least squares. All right, let's show the code. So don't need to copy, guys, because I've just dumped this test pseudo inverse Python in the adventure. This line of code is let me change the color to green. So see, normal X, I call it normal X, is equals to, and you can see A transpose here, dotting with A. So it's A transpose multiplying by A. Take the inverse of this matrix, multiply by A transpose B. Okay, so you realize that actually writing Python is not so difficult. Writing MATLAB is even easier. Let me show you the MATLAB solution. Where's my MATLAB? Here. Okay, chat room. I can't see your chat. Wait. Oh. Chats. I can't see your chat. Can something? Can someone ask the question, please? Is there a difference between mp.a dot? Ah, okay. Yeah, I never like mp.a comma b a dot. I don't like that because it's not intuitive. I prefer a ampersand b. Okay. Because you look at the MATLAB's solution, it's so much cleaner, right, guys? Can you see? So much nicer than Python. X1a equals to P inverse A times B. X1b is equals to inverse of A prime, where this prime stands for the transpose times A. So in MATLAB, the matrices and vectors are first-class citizen, while in Python, they are not. So then you must be wondering, why am I asking you all to do Python today? And why not continue with MATLAB? Like, because that was what we have done in the past. And the real reason is that Python is the most important machine learning programming language in the world today. Okay, guys? Of course, MIT just said it's Julia, but we don't care. We just use Python.
Oh, they're not here.
Okay, enough? Have I answered your question? Actually, it's very strange, teaching with, I'm just talking and I can't see you guys at all. Yeah, but if if you can let me know. Yeah, I'll be actually very grateful. Anything else, guys? Enough? Have I answered your question? What would yeah, please don't do A times B, okay? Yeah. A times B wouldn't work. All right. It's a Python eccentric syntax. A times B, that star thing doesn't work. Okay. I mean, if actually I were to do it, I would have done it this way. I would have preferred it this way. A transpose multiplied by A. And then let me see my solution. So P4, P3 is by pseudo inverse. This is the solution. And P4 is by this guy. Can you see it's the same? Okay, I like the ampersand because the ampersand just reminds me of matrix multiplication. If you do this guy, I think you get wrong answer. Okay, yeah, see? NP multiply also might get you the right answer, but you're only confusing yourself after a while. So I prefer this guy.
No, you fucking.
Okay. So let me run again. Yep, see? So my solution is correct. Now, so you'll be wondering, why do I bother about P inverse if it gives me the same answer, right? And the real reason is this. Okay, maybe Cheryl, yeah, here's your answer, or here's your question. I'm going to change A from the first row to the second row. In the second row, you'll notice that my A is actually, what's my A? Let me see. My A is first column and the second columns are dependent. I can get the pseudo inverse. 3 by 2, I get a pseudo inverse 2 by 3. Wow, but this is hopeless. A plus times A is no more the identity. Can you guys see? So it becomes the identity only when the columns of A has independent columns. So you must watch out. All right, then we keep on doing this, and then you realize that I can solve everything by P inverse. But when I try to do this, remember that this is a problem now. A transpose A only has dependent column. A transpose A is going to become singular. When you try to find the inverse of a singular matrix, then it dies. Okay? So that's the problem you'll see. Where does it raise? Yeah, it raises the singular matrix linear algebra error. Okay? So this lab is all about going through this and then, you know, answering the different problems that you will encounter if A has dependent or independent columns. Okay so far? So actually I'm here to answer the lab today maybe. So instead of answering the last question. Anyone got any problems? Maybe I'll answer exactly what, I'll answer Cheryl's question. How's that? Let's read the question properly. Hi, Prof. Could you go to part H? Okay, part H first. Can we use the normal equation to solve for x in this example? Okay, when can we use the normal equation? So So I'm going to find the lecture notes for you. Wait, okay. So where's my lecture notes? All right, please hold on a minute. Let me.
Oh, okay.
All right, here. Okay, guys, please look at this slide 7.1.5. And to answer your question, there are 3 ways, or actually there are many ways to solve for this. And here I show you P inverse in the lab and inverting the normal and using QR. But when do we cannot use here is when this guy is not invertible. And so this is the when we cannot use when this matrix is not invertible. So when would this happen? Can we use a normal equation to solve for x in this example? So it depends on which x I'm giving, which a I'm giving you. Okay, guys? If I'm giving you a, such a ATA has an inverse, then of course. But if I give you an a that has dependent column, then no. So you need to go through this tutorial. You need to go through this question. And when would this happen? Is when the columns of A are linearly independent. Okay. So, Vinay, have I answered your question? What is the justification we need to prove? You need to prove that columns of A are independent. That's one way.
Yes, Prof. Thanks.
Okay. The second way is the rank of A. The rank of A is equals to the number of columns. That's another way. Actually, there's so many ways. So you know, you never run out of ways. Prof, if A is invertible, would it guarantee that A transpose A is invertible? Ah, friend, Chuan Song, A is not sometimes not even a square matrix, my friend. Right? We are playing A is a 3x2 matrix all the time. But if, of course, if A is a 3x3 matrix and is invertible, then A transpose A is definitely invertible. But most of the time, A is not a square matrix. So A is a rectangle matrix. Okay, Chuan Song? Okay. All right. So can I answer Cheryl's question now? Which is, oops, which is this. Evaluate endpoints around the least squares when it exists to show that it gives the best solution. Okay, so what am I asking for? I'm asking for wait, guys. Okay. Let me find the slides, which it will show you the correct interpretation. And it is here in this. Okay, so imagine the question is asking you, you have already found the least square solution. And then now you go and find different x around your least square solution and show that the error is bigger than your least square solution. So how to do that? So go to this guy, go to this slide, And then now start to understand the problem. This is the columns of A. And once we have found X hat, we have landed ourselves here. And then this is the error. This is B hat. Error is equals to B minus B hat, the norm, yeah, the length. And we are saying that this length, the error is the smallest because B is sitting right on top, is perpendicular to B hat. Okay. Now then I say, go and find 10 other points around X hat. Okay, you read the question very carefully. It says, evaluate 10 points around the least square solution. The least square solution is X hat. So where is X hat? So X hat is our friend here. So find another point. So maybe this is, let's call this X1. X1 is equals to X hat plus some value. Delta, some value you want. This is X1, this is X2. How about this guy? This is X2. This guy is X hat plus some delta X1, delta X2. We don't care what delta is, just some small value, 0.1, 0.01, whatever you want to find. But what happened is that you can find, and then you basically you're evaluating here, you're evaluating here, you're evaluating here. And then you realize that any other point that you have tried to evaluate, the error is always greater than the solution found using the least square solution. Because this guy is always the nearest guy. And when the columns of A is unique, AX hat only will land in one point. And the surface of the error is very, very pretty. It is what do you call that? It is a cone, and it only has a global minimum point. And the global minimum point will tell you what is the exact value of X1 and X2. Or if you plot it here, you have one global minimum point, and around all these points are equidistance error. Yeah, so that means you could find, you know, different points along with different X1 and X2, and the error, this error will be the same. Okay, maybe you can find another point here, this error is the same. Or this point here, the error is the same. Okay. All right, Cheryl, have I answered your question? Do you know how to do this now? Okay, good. Okay, Daryl. ATA is not invertible. Then wouldn't we still be able to find a general solution? Ah, very good. Okay. Yeah, it's a difficult question, huh? So the Daryl asks, what happened when ATA is not invertible? Okay, let me. Wait, let me. Okay. All right. In your tutorial 7, question number 3, you realize that A has dependent column. So even though he is 1, 2, 3, 4, 5, 6, he's 6 by 4, his rank is only equals to 3 because only 3 columns are independent. I'm still showing my screen, right, guys? Yes? Okay. Because you realize that the first column is nothing but the second, third, fourth column added together. So this is the problem. So A has dependent column. What about A transpose A? So this guy is a 6 by 4. So this is 4 by 6. 6 by 4. I get a 4 by 4 matrix. And a 4 by 4 matrix is a square matrix. And we hope that A transpose A inverse exists. But we know that the rank of this guy is only 3. Therefore, although we have a 4 by 4 matrix, only it has rank 3, therefore it's not invertible. Okay, and then how do we solve? Remember, in question 3, we are not, you know, we couldn't solve for the normal equation A plus A transpose A inverse. So what do? We resort to the good old Gaussian elimination. And through the Gaussian elimination, we know how to do the parametric form of X. And then now we see that this is one particular solution, and this is the null solution, and this is the general solution of X hat. So Daryl, have I answered your question? Daryl? So why should we use pseudo inverse if we can just get this? Oh, because pseudo inverse, you do it in one line, right? So is pseudo inverse implicitly doing Gaussian elimination on the dependent matrix? Wow, you guys are asking difficult question. Okay. So first, I want to answer Daryl's question. Why should we use pseudo inverse? Because actually, there are many ways to solve the least squares. So when A transposes, one way to do is the Gaussian elimination. 2 is to use the pseudo inverse. There should be other methods, right? But so what are they? Well, okay. So first, Daryl, you must understand that why should we use pseudo inverse if we can just get this? You can, depending on which one you prefer, actually. You can, but I think the solution would be identical. In fact, I would always prefer the pseudo inverse. So now Daryl is asking, if we use a pseudo inverse, which solution we get? Okay, Gaussian elimination only tell you this, right, guys? The particular solution plus the null solution, and then you realize that you can change whatever x4 is, including 0. What you realize is that the pseudo inverse will give you only one of the solution, but this solution has the smallest something. Okay, this is very advanced, so I think you can forget about it. It has the smallest norm x, in addition to being the least square solution. Okay, so among all the x4 that you can play with, then you will find the small, such that this whole thing become the smallest. Okay. Now, Vinay's question is also difficult. Pseudo inverse is not doing Gaussian elimination. Okay, so pseudo inverse is a very big deal. I think when we reach SVD, then you'll do pseudo inverse. Okay, so let me Google for you. SVD and pseudo inverse realization of each other. I mean, they are cousins. Yeah. To get pseudo inverse, we use SVD to get it. Okay, later on, we will show you how. All right. So this is A, and this is the pseudo inverse of A. All right, but never mind. We'll reach pseudo in. I mean, we are asking you to use pseudo inverse as a code now, right? We don't care how you get pseudo inverse, but when we reach SVD, you will learn how to use pseudo inverse. or how to get pseudo inverse. Okay. Did I answer your question, Vinay? Thanks, Prof. Okay, great, thanks. Did I answer your question, Daryl? Just mind blown. Okay, clear. Okay, but maybe, so Cheryl, I've also answered your question on how to do the lab, right? So if you really do not know how to do the lab, you'll realize that the MATLAB solution is complete. That means you just go to run MATLAB or you read the MATLAB solution one by one, and then you are basically translating your code to Python and make it happen. And then in the quiz, what we'll do is we'll throw you another A, and then you guys can go and figure out different values of. Do we need to know chapter 8? Nope, you don't, because it's only least squares. The only thing you need is pseudo inverse, which is just P inverse. Yeah. Yes. Yep. So just chapter 6 and 7. Yes. And the quiz will be just chapter 7 and 8, I think. Yeah. Okay. Yeah. Actually, guys, yeah, I've been, yeah, I've only saw you once really physically in the quiz. So it's very strange this year for me. Do we get to know previous quiz mark? Yes, as soon as we are marking them. So yes, we will try to mark them soon and we'll release. But I think everyone did very well because I guess the only tough one was the last question. Will this lecture be uploaded by tonight? If you want to, is it necessary? Mintit. Do you want it to be? Because I'm mumbling most of the time. Yeah, okay, I'll upload this. Maybe it's useful. Actually, there's a lot of information you give for your chapter 8 slides. Are we supposed to know everything? Chapter 8 slides. Chapter 8 is for, yeah, chapter 8 won't affect your lab, so don't worry about it. Really? Is there a lot of information, Daryl? Okay. Yeah. I guess, okay, I guess everyone is worried about how much you all have to study. The answer is, if you can do the tutorials, then you'll be fine. Yeah, so just do the tutorials, at least do the tutorials. You saw how, I mean, that in the quiz was relatively straightforward. So we'll also be doing that kind of, you know, 2x2 matrix, 3x3 matrix kind of problem. Yeah, so just do the tutorials, guys. If you can do the tutorials, you'll be fine. Yeah. Actually, yeah, I'm quite happy that you guys are asking these kind of questions and I'm answering it this way. Otherwise, it's actually quite I don't know how to describe. Just actually, I'm talking to myself all the time. Okay, Ken. So we are at 3:24 now. Any more questions, guys? No. Okay, so I will upload this, but please don't complain because I'm not going to edit this. Okay, so I'm just going to just release it like that. Okay. Prof, for part A, what's the point of showing P inverse A and A P inverse? Oh, P inverse times A and A times P inverse? Is that, Chuan-Song, is that your question? Okay. Okay, let me explain that.
Yeah, only we can push it by using OT.
Oops. Pseudo inverse wiki and So don't get confused. Huh? The word pseudo inverse is more Penrose inverse, same. And we are talking about the problems of so when things become too complicated, don't bother about all this, okay? But we were talking about this problem, I think. Yeah. So you realize that if A times A plus is identity, but then you realize, hey, it's very strange, huh? So pseudo inverse is nothing, or it's very close to inverse, but a little bit different. Because A times A plus times A equals to A. You would have thought that A times A plus is I, the identity, right? But it didn't need to be the identity. As long as A times A plus times A equals to A, it satisfies the pseudo inverse criteria. Can you see now? Yes, Prof. Isn't it sufficient to just prove one of it is equivalent to the normal equation? No, nothing to do with the normal equation. The pseudo inverse has nothing to do with the normal equation. The pseudo inverse is actually what's his name? Okay, maybe I wait. Let me show you. If I can find Andrew Ng again. Where's my Andrew Ng? 4 ways. Okay. Sorry, let me.
Help lah, cibai.
Let me show you Andrew Ng, if I can find him. Oh, I can't find Andrew Ng. But if you look at one of the video by Andrew Ng, where he talked about pseudo inverse, his explanation of pseudo inverse is this. It's just a more stable version of inverse. Okay. And if you do not, and as engineers, if we every time we look at the word inverse and we replace it by pseudo inverse, it's going to work. And that's one way you can think about it. Of course, if the question is why does it work, then it's a very complicated affair. Okay, but pseudo inverse and inverse is not talking about the normal equation. It's trying to solve the inverse of A. That's all. Okay, I think for those who need to leave, it is okay. So I would upload this and then please tell your friends who are not here that I have already uploaded the code into the, what do you call that? Into the adventure. They should be looking at test P inverse Python. They should be installing deal. Okay, you don't want to have your environment installed in the lab because it will cost you 1 mark. 30 minutes is 1 mark. Okay, try to get it done at home. Part A was trying to find the x hat through P inverse normal is equivalent. It's not equivalent, it's the, it's in fact, you'll give you the same results because A has independent column, that's all. If A has independent column. If A does not have independent column, then P inverse will find you a solution, but the normal equation will fail. 传送. So they are not equivalent for all cases. Okay. Then part 2 tutorial, please look at the 7 support. You realize that I have handwritten my notes here and you can take the answers from here as well as go. So I've written all the answers and you can pick it up from here. Okay. All right. So then with that, maybe I'm going to end and then I will upload the the what do you call that, the Zoom recording online. Okay, so take care. I will see y'all again, some of y'all in FS3 in the lab tomorrow. Are we starting on tutorial 8 next week? Yes, because I will record question 6 online. Okay, can. Okay, great. Take care. Bye. Welcome. Bye, guys.